Okay. Hi guys. So this video we'll be talking about a paper by the title representing scenes as neural radiance fields for view synthesis, which is NeRF for short. This paper was released in August 2020 by the mentioned authors. I am Mustafa and I'll be happy to take you through it. Okay. So today, sequence of this presentation, we'll go first through the problem statement, which states which question this paper is trying to answer. Then we'll go dive a little deep into the related work, which I see it's a bit necessary to understand the concepts that are later explained in the paper. Then we'll get to know what is NeRF. Then we'll know some of the optimizations that were used and explained in the paper on the basic idea of NeRF. Then we'll go a little deeper into the implementation details, how NeRF was implemented. And then we'll go into the results and comparison with previous work, which the comparison is done with some of the papers that we would have discussed in the related work. Then finally, we'll go through the conclusion and the discussion, and the references are mentioned at the end of the slide. So let's get started. So first, the problem statement. As presented in the abstract of the paper, the authors they mentioned, so we present a method that achieves state-of-the-art results for synthesizing novel views of complex scenes by optimizing an underlying continuous volumetric scene function using a sparse set of input views. Okay, so what does that mean? This actually raises more questions than it answers. So in the introduction, it's a bit more clear. So in this work, we address the long-standing problem of view synthesis in a new way. Okay, so this is a bit clear. So now the question is, what is view synthesis? For anyone who doesn't know about this field, including me, I didn't know actually. So view synthesis, as per Wikipedia, currently it's a study branch of computer science research. So view synthesis aims to create new views of a specific subject, starting from a number of pictures taken from a given point of views. So the basic idea of view synthesis is that we have a source image of an object or a subject, let's say, from a certain camera pose. So it's looking at the subject from a specific angle and position. And we have another pose, a target pose. So we need to synthesize what would be the target image, the resulting image, if we look at the same object from a different pose. So this is like the novel idea. Now, in NeRF, it's, as they explain it, not so much different from the novel idea. It's just we have a set of input images. It's not just one image. So we have a set of input images. NeRF system somehow does the optimization that renders new views that are different from the input images. So the input images look at the object from different angles and positions. And for example, we need to render how would this object look from an angle or a position that was not presented in the input images. So basically, this is the idea of view synthesis, which this paper is trying to solve this problem. Okay, so going to the related work. Now, there are multiple there are multiple ways that other researchers try to solve the view synthesis problem. Now we can distribute them in different categories. So the first one we will discuss is neural 3D shape representations, which is basically using neural networks. So it is the representation of continuous 3D shapes as level sets by optimizing deep networks that map XYZ coordinates to a signed distance function or an occupancy field. So this deep neural network, it maps a coordinates x, y, and z to a something called the signed distance function. So this is the first paper we'll discuss. It's talking about the idea of signed distance functions. So what is a signed distance function? A signed distance function is a continuous function so that for any point in space, in XYZ space, this function gives a value, the output value. It's either negative if this point is inside the object, or it's positive if this point is outside the object. And the magnitude of the value, so this is a sign of the output. Now the magnitude of the output would be, it depends on how far this point is from the closest surface of the object. So it's pretty basic, simple. Here we see some kind of heat map. So ideally, on the surface of the object itself, the signed distance function value would be 0. Here we see in the red area, this is where positive values grow stronger, and in the blue area, this is the negative values. As we go in the middle, near the middle of the object or far away from the surface, the color gets darker, the value gets less since it's negative. And near the surface, we see that they are around white color, which is a smaller value, negative inside, positive outside. Okay, so this is for signed distance functions. For the second concept, which is occupancy field, it's not very far away, a little similar. The difference is that we have now the output. The input would be an XYZ coordinate as well. Now the output would be a probability function, probability, when it's between 0 and 1. So it would give a probability of whether we are inside the object or whether we are outside the object. And on the surface itself, so f of theta here, it represents the network. So f of theta of a certain point on the surface of the object, it will give a value of tau. So something between 0 and 1. So this is similar to a binary classification neural network that just gives a value output between 0 and 1, but it indicates where this point lies relative to the subject that we are trying to solve or trying to represent. Now, what are the limitations of these methods? The problem is that they need to be trained on 3D geometry datasets, such as ShapeNet. So ShapeNet is a huge dataset of multiple objects. It has the 3D representation from all angles. So this is, I guess, it's pretty difficult to come across. So this is valuable data. I don't think it's available for all kinds of objects. So this is a big limitation for these methods. Now, the next kind of methods, which does the same thing, but using only 2D images. So the first method we will discuss is differentiable volume rendering, DVR for short. This was also presented in the related work in this paper. So DVR, just building on what we previously discussed in the occupancy fields paper. So this is something a bit similar. We have the surface of the object or subject that we are trying to represent at surface the function, like I said, the probability equals to tau. Inside the object, it's more than tau. Outside the object, it's less than tau. Okay, now just the difference here in differentiable volumetric rendering is that it doesn't just, it trains two networks. One is f of theta, which represents the 3D shape itself, and t of theta, which represents the texture at the point that we are trying to render. So here, when I have an image and I have a ray, or here this represents the camera, I'm trying to look at the object from a certain angle with a direction W through. So this would be projected on my image as a pixel U, and the network, the first network, would estimate this distance value from the distance from the image to the object, and the second network would estimate the texture at this point, and this would result in what would be here in this pixel. Now, the problem with this method is that it needs to access ground truth depth images. So here, in order to be trained, you need to train it on images that have depth maps. At each point, the image, it's not just a 2D image, it's a 2D image accompanied by some kind of matrix that indicates at each pixel how far is the object from the input image. So, which is also something difficult to come across. The second method, this is an important one because this is one of the methods that would be compared. We will compare the results of this method against NeRF in the results and comparison section. So this is scene representation networks, SRN for short. So scene representation network is a bit more complicated. Just to go quickly, this is like the full system representation. I'll just go quickly through it. Now, the idea here is that we have a scene representation network called phi. Now, this network, it gets as an input XYZ, which are the coordinates, and it maps it to a feature vector. So this feature vector can be trained on anything. It can be trained on how much light is present at this point, what is the reflection, whether it's transparency, whatever. Also, the distance of the object from the image. So this scene representation network is trained, it outputs a feature vector. Now, the feature vector here, it goes into the new renderer part of the system, which is this dotted part. It uses an algorithm, it's called ray marshing. This algorithm, it starts with a point near to the camera, let's say, and it would assess the scene at steps of D. So these steps, we call it the depth. So it would first, for example, it was assess the scene, it would output a feature vector at this point, and then through the ray marshing algorithm, this would output a new depth. So it would tell you to take a step, for example, like this big, move closer to the object, and then reassess at this new ray, which is a new distance from the object, output a new feature vector, and it goes so on until it estimates that it has reached the object. And when it does, here we go into the pixel generator part, which we put the final input through the scene representation network and output the feature vector, which would contain the color, the texture, like I mentioned, could be whatever at this point. And this generates the color or how this pixel would look like. So this is basically the idea of SRNs. A bit complicated, but It's more efficient for sure. Now, this way it would be trained on 2D images and it would render outputs on any arbitrary view of the object that was presented in the input images. So what are the limitations of these methods? So far, they have been limited to simple shapes with low geometric complexity. So it results in over smooth renderings. Like you see, these are examples from the SRN. These are examples from DVR networks. So again, they are still simple shapes, simple textures, not very complicated geometry. So this is their result. Now, moving on to the next kind of approaches that try to solve this problem of view synthesis, it's using image-based rendering. Now, this is a bit different because it depends on giving a dense sampling of views. So it needs a lot of images in order to generate new views of this, let's say, novel view, like they mentioned. It can be constructed by something called simple light field sample interpolation. So this is like a method that tries to calculate the novel view based on some function or equation of the input from the input images. So here, the first paper at hand, this is a pretty old paper. It's from 1996, but it's important because I think it's one of the first that used this method. So it's called the Lumen graph. Now, what is the Lumen graph? It's a subset of plenoptic function that describes the flow of light in all positions and all directions. So it's a 5-dimensional quantity describing the flow of light at every 3D spatial position, X, Y, and Z, for every 2D direction, phi and theta. So they discuss here the computational methods for capturing and representing this function. So they have a dense input of images, and they try to derive analytically. We're not talking here about neural networks. So this is like some analytical derivation in order to come up with some function that would represent this scene. So when you give this function any x, y, z, and a viewing direction, which is represented by phi and theta. Now, the viewing direction, just since we mentioned it here, it represents where the camera position is and what direction is it looking at the object. So when you're giving these two values, this gives you an idea what ray you are trying to estimate. How is the camera looking at the object? Now, this is for the Lumen graph. There were other methods that use sparse view samples, which sparse means not dense. It's not too many inputs. I will not discuss them in details since they not really related to NeRF or the results and the comparisons that will happen later. However, there is something called mesh representation. However, they are difficult to do gradient-based optimization using neural networks. And they require something called a template mesh with fixed topology to be provided as initialization. So it does train on images. However, you must give it some kind of 3D template of the object before you optimize the neural network. So this is just the basic idea. Now, the second one, which uses sparse input views, it's called volumetric representations. Now, this is an important one because we will use here two of the papers presented in the related work section. So the first one is called local light field fusion, LLFF. Now, basically, the idea, without going into too much detail, it gives a guide on how to capture images. So from certain locations, you look at an object from certain angles, and here they're using normal smartphone images. So they give you certain locations to look at an image. Now here, the deep learning part, the neural network part is trained in order to expand each of these images into layered representations. So a layered representation means at a distance x, the objects hitting the image at this distance is whatever, and at a closer distance, a closer distance, a closer distance, and like that. And when you try to render a new view, some new camera position looking at the object, the renderer, it's called blending. So blending, it like takes the second layer from this image and the first layer from this image and third layer from this. It depends on the camera direction and position. This is called blending in order to represent the new novel or the new view that was not presented in one of the input images. So this is local light field fusion. The second one, which is also important, which is neural volumes, NVs for short. Now, neural volumes, their method consists of 4 steps. So you have a multi-view capturing system. Here, the object, I believe this is one of the authors of the paper. So they capture views from different angles. Now they encode networks, which is similar to transformers in neural networks. So you have an encoder that you feed the images to. It gives you a Z representation, which is an encoded representation of the scene. Now, and after that, you use a decoder in order to map this scene into a 3D space. And you use, and again, ray marching, which is in order to represent for each point in the 3D space, what would be using the decoder for the neural network. It would query the network at each point using this ray marching algorithm in order to know what would be the color and the density. So there is an RGB, which represents the color of this point, and alpha, which represents the density at this point for each point in the 3D space. Then it would render the new view, and again, the training would happen, that they would compare the final reconstruction with the target image, which they have in the dataset, and I guess they back propagate through the network in order to optimize the weights. So this is how the training is done, and it's understandable that inference is done in a similar way. Now, here, just without even looking, so I would assume that this kind of representation, it would take a huge amount of memory because you need to represent the whole scene, every pixel, or here we call it also, this is one term that you need to be familiar with. It's called a voxel. So a voxel is a pixel in 3D space. So anyway, moving from neural volumes. So at this point, we have finished what related work has been done in this area of view synthesis. So now we will move on to what is NeRF. So NeRF, neural radiance field scene representation. So it is a scene that is represented as a 5D function of location XYZ and a viewing direction theta and phi. Now we already explained what theta and phi is, and XYZ is understandable. So the output would be a rendered image. So it's represented as a color, RGB, and volume density, similar to what was just explained in neural volumes. So this is the input, this is the output, pretty basic. How it is done, I guess you guessed it already, through an MLP neural network, F of capital theta. So it gets as an input X, which is the coordinate vector, XYZ, and D, which is the viewing direction vector, which represents the camera position and viewing direction. And it outputs a color and a volume density at each pixel of the new image that we want to generate of a novel view of the object. It would output at each pixel what is the color, what is the density at this point. So here, the authors, they mentioned something, it makes sense. It pretty makes sense. It's called multi-view consistency. So multi-view consistency, it says that here I'm training a neural network on some inputs in order to generate some outputs. Now, it makes sense that for a certain point in space at location XYZ, the density would not change. So whether I look at this point from one angle or from another angle, the camera is near to this point or further away, the density shouldn't change. So they mentioned some design perk that they used here, which is they use the coordinate vector, only the coordinate vector, to train the network to output the sigma, sorry. And the color output would be from both the coordinates and the viewing direction. So this actually, it makes a lot of sense. So the color would depend on both the viewing direction and the position. However, the density, it would just depend on where is this location that we are trying to assess. Now, this results in an important feature for NeRF, which is called view dependence. So here they used it as example, this ship, the 3D ship representation. And we see that looking at the ship from two different angles, we see here a point in the area around the ship, which is like water surface or something. So at this point, from this angle, we see a certain color. Now, at the same point, from just a different view, we would see a different color. And we see here the difference in colors of these 2 points. Now, they are the same point in space, just looked at from different angles. Here also, we have at the front of the ship, we have some point that when looked at from this angle, it would have this color. When we look at the same point from another angle, it would have a different color. So here, colors would differ. Okay, so this is a representation. This is from their website. So it shows how view dependence differs. Now here we have, this is the same scene, just here is a fixed, like when you look at a fixed scene representation, how looking at the same objects from different angle would differ in their, like, let's say lighting and reflection. And sure, this means different colors for each pixel and the generated image. So it's pretty cool. Okay. Now, rendering, which is the output, it's just a 2D image. So the rendering result is a 2D image. This is after we train a network. This is the output that we want from the network. So how do we do that? So as explained before, we have a 5D input of position and direction, X, Y, Z, theta, and phi. So this is an arbitrary point that we use as an input to the network, f of theta, and it outputs a RGB and sigma, which is the color and the density at this point. Now, the rendering part, which is, let's say, for example, that this image is the one that I want to generate. So the volume rendering section, this would look at the function of sigma, and it would see at each point what is the RGB and sigma value at this point. And somehow we need to know the end result, which is the pixel. What would be the color of this pixel exactly for this ray, which is the result of this ray? What would be the color of this pixel at this point? And this is the volume rendering. This is the rendering function that we mean. We need, for a given ray, we need to have an output color for this ray, because this ray on our rendered image, it would represent 1 pixel. So how would this function be? Now, we need to remember that this is a neural network, so we need to back propagate through these values, because in the end, we would take this color and compare it to the ground truth, because this is how the training is done. So this is one of the training images, for example. I would use the network to output the result, which is this image, and then I want to assess it against the ground truth, which is the input image. So I need to backpropagate through this. So in order to do backpropagation, this function needs to be differentiable. So now, what are the functions that would be used? So we have first the function for the density. This is pretty basic because it's just the probability of a ray terminating at an infinitesimal particle at location x. So this is just sigma of x. It's a probability there is something there or not. That's it. As you see here, it pretty much looks like a probability density function. So this is the sigma function. This is the magnitude of this curve. Now the color, which is the second output, this is the expected color of a camera ray R. So when we see here, for example, this is ray 1, which here we are looking at some kind of Lego tractor. So when I'm looking at it from this angle, I would just like go through empty space, and then when I hit the tractor, the sigma function would rise because there is an object there is some density, and then it would fall back down. Looking from ray 2, I would be looking at the tractor from this angle, so there is some kind of fork and some kind of here the body of the tractor which the driver sits. So I would be looking at it. When I look at it at the density function, I would see the density rise at the fork area, and then it would fall down. There is some empty space here, and then it would rise again. And we see that at each point, there is a certain color. So there is a color difference between each point here. And the rendering function takes this output at every point and gives you the final color of the pixel when you are for this ray, which represents this ray. So how this is done, it's done by integration. So C of R, which is the color of the ray, is given by this function. Now, this function looks complicated, but we'll break it down to understand what every component means. So first, we integrate from Tn to Tf. So Tn and Tf, they're basically near and far. So we are starting with a near point from the camera and ending the integral at a far point. Okay, this is basic. Now, the first part, which is capital T of the point T that we are assessing. So capital T is called the accumulated transmittance along the ray, which is the probability that the ray travels from T near to T without hitting any other particle. So this is capital T function. It's an integral from T near to T, the point that I'm assessing, of the sigma function of this ray. So this basically represents the transparency of the volume or the media that the ray traveled until it reached the point T. It would hit something along the way, or maybe it would hit something, but it's transparent, or how transparent is it? So this basically what this terms means. Is there something along the way or not? Next, sigma of the ray at point T, this is basically the density at this point. Finally, the color, this is the color of the ray R at a distance D. So here, this is from the previous slide, we have this graph just enlarged. So we have here the sigma function, and the color, like I said, it changed depending on the distance of the point from the starting point. So color, it's a function of the ray itself and the distance. So these are the components of the integral. So basically what we're doing here, just to explain in plain English, we are integrating along this line. Is there something there or not? How dense is it? Is there something transparent along the way or not? Or there is something blocking the view at all? And what is its color? So we do an integration on this curve in order to know what the projection of this ray on the output image, what color it would give on the projected pixel. I hope that explains it. So now, in order to do this integration, sure, we would need an approximation because I don't have this function as a continuous function. I just have a neural network that is trained and I assess each point individually. So basically, we are just sampling number of n points along each ray and assessing the function of this output. However, when you think about it, sampling at n intervals, it would heavily depend on what is n, and it would result in lower resolution of the output images. So in order to do that, or to overcome that, they use a method called stratified sampling. So stratified sampling is that they partition the area or the length between t near and t far from the first point to the last point. They partition it into n evenly spaced bins. So between this point and this point, this is one bin. Between this point and this point, there is another bin. And they draw one sample uniformly at random from within each bin. So within the first bin, they take a random sample between these 2 points. We don't know where this sample would lie exactly. It's just randomly chosen at the distance between these 2 points. Now, what this would do, this way the MLP is evaluated on a continuous set of positions over the course of optimization. So this way, there is no discrete points that every time the MLP would be assessed against. It would be similar to a continuous function because every time we sample a different point, not discrete points. So I hope that's clear. Just to look at the equation. Also, it looks complicated at the first sight, but it's pretty easy. We just hear how to sample t of I. So we choose between two. This is the starting point, and this is the ending point. So here we have t near, which is the starting point near the camera. And so we have the first point, which is t4 minus t near, divided by n, which is the number, multiplied by I minus 1, and then the second point is multiplied by I. So basically, the first term represents, for example, this point, if I equals 1, and here I equals 2. So the first term represents this point, the second term represents this point, and here we would sample a random sample between the 2 points. That's basically what this equation means, okay? Now, finally, in order to derive the final equation that we would use as the volume rendering function, they use something called a quadrature rule, which is inspired by this paper by Max. So what is this rule? It states that the opacity alpha of a voxel of side L, voxel, like I mentioned, it's a pixel in 3D space, viewed parallel to one edge is given by alpha equals 1 minus e, our negative tau L. So tau is the density of the voxel. So given that the density tau is constant inside the voxel, the opacity, which is the, let's say, a proxy of the density of this voxel with a side length L. So voxel is a cube, one side its length is L. So this is how the opacity of this voxel would look. So they use it to represent the equation. Like we mentioned in the last slide, we use here a sum instead of an integral because we do sampling. So we sum from I equals 1 to n, which is the number of intervals. T of I, capital T, this is the same function like we used before. And sigma, instead of sigma, we would use here this quadrature rule, which is 1 minus e power negative tau L. Here, we replace it with different values. I will explain them now, multiplied by the color at the point I. So just to explain these new terms, delta, this is T of I minus 1 minus T of I, which is basically, this is the voxel side. So here this is a distance between one sample point and another sample point, which would represent the side of the voxel, which is here mentioned as L in the other paper. And T of I, capital T, this function we already looked at it before. However, after doing these substitutions, we would integrate, we would sum instead of integration from j equals 1 to I minus 1, which is the point before the point that we are assessing, sigma of I, which is density times delta of I. Here, we're just using the same terms, just in terms of sum instead of integration. So nothing pretty much different from what was mentioned before. And this is the final equation of the color of the ray, how it is estimated. Now, this is the vanilla NeRF, we can say. Now we will look at what optimization techniques were presented in the paper on the standard idea. Now, to achieve state-of-the-art quality, NeRF uses two improvements. First one is called positional encoding of the input coordinates, which this assists the MLP in representing high-frequency functions. So this is encoding of the input variables in order to represent high-frequency changes in the inputs. I will explain that now. The second improvement is hierarchical volume sampling, which is a procedure that allows us to efficiently sample this high-frequency representation. So it just we would here represent the inputs in higher coordinates using some encoding method. And the second improvement which is needed is how we would sample from these high-frequency functions, high-frequency inputs. That's what I mean. So let's go through the details of each one. So first, the positional encoding. The driver here is having the network f of theta directly operate in x, y, z, theta, and phi input coordinates. It will result in rendering that perform poorly at representing high-frequency variation in color and geometry. This actually makes sense. So I have for every input coordinate directly operating on them. You can think of this the same like when you do let's say, a regression function. So when you use the first order equation, it's different. When you want to capture more complex representations, so you would use a higher order. For example, instead of using x multiplied w plus b, you would use terms of x squared plus x plus b, something like that. So this is basically the same idea. We would just encode the inputs in order to represent the more minute and small details in the scene. So this was due to two findings that were represented in this paper. That deep networks are biased towards learning lower frequency functions. So this is known. It makes sense. Deep networks are biased towards learning lower frequency functions than higher ones. Now, mapping the inputs to a higher dimensional space using high frequency functions before passing them to the network enables better fitting of the data that contains high frequency variation. Okay, so how it is done? This is done by representing f of theta as a composition of two functions. So we have f dash of theta and gamma. So what is each one of them mean. We have f dash of theta. This is the learned part, which is simply, this is just our network. This is the M of P. And gamma, this is a fixed function. It's not learned. So what is gamma function? Gamma of P. P here represents one of the inputs that would be in the input layer of the network. It will be represented by these terms. Instead of just giving the network an input P, we would give it sine 2 to the power of 0 pi multiplied by P, cosine 2 to the power of 0 pi multiplied by P, and so on until, let's say, this is gamma of an equation of order L. So until we reach sine 2 power L minus 1 pi of P, cosine 2 power L minus 1 pi of P. So we're starting from 2 power 0 to 2 power L. So this is like an equation. Just think of it as a polynomial equation of order L, for example. This makes it easier. Now, how it is done, I think it's understandable. So gamma of P, it's applied to normalized inputs. So first they normalize the inputs to lie between the interval of -1 to 1. And they use L equals 10. So they use an equation of order 10 for the 3 coordinates, which is x, y, and z. And they use an order of 4 for the viewing direction, which is theta and phi. This also makes sense because when you think of it now, one location in the object XYZ and another location very near to it, another XYZ, it would have more variation than looking at the same object just from different viewing directions. Now, they both would have variation. This is why we use positional encoding for both of them. But the variations in the position would be probably higher than the variations in the viewing direction. So this is why here a higher order is used to encode the coordinates. Now, the second optimization, which is hierarchical volume sampling. This is actually pretty smart. So sampling the network at points n along the array is inefficient because there is a lot of free space and occluded regions. So they do not contribute so much to the rendered image, but however, they are still sampled every time we do an optimization step. This is true because from the starting point t near till t far, until we hit an object, there is a lot of free space. So why I would need to have a lot of samples in that region? Why I don't just skip it and go to the important area of the scene where the object lies? Here I would need higher frequency of samples. I would need more samples in order to better represent this object. So how they do it? This is inspired by also another paper, which talks also about volume rendering. Here they train 2 networks simultaneously, a coarse network and a fine network through the following steps. So we have 2 networks, coarse and fine. Coarse is the one we start with. So we have n coarse, number of samples, and c, location, which is using stratified sampling, the method that we discussed a few slides back, which is instead of fixing certain sample points, we would randomly choose between each two points as an interval. We would randomly choose a point in between. This is stratified sampling. So we do a number of NC locations. Now we calculate the color equation, which is C coarse. Now this is the same color equation that was before. Instead, we just replace the first 2 terms with W, which represents, this is the weight multiplied by the color. Now, if you remember the weight, the W, the first 2 terms are capital T, which represents the transparency or if there is something in that area, multiplied by the second term, which represents the density. So density of the point where we're standing. So this is W. So it's the weight multiplied by the color. Now, afterwards, we normalize these weights. So we divide W at each point by the sum of all W's from J equal 1 to NC. So for all locations, we get a probability density function by normalizing the weights. So we get a probability density function along the ray, which areas that are not free space will have higher weights. Areas that are free space would have lower weights. So after we calculate this function, we use it to sample another set of n fine samples. So this is a number that is more than n coarse. So we derive number of samples using inverse transform sampling from this probability density function. Inverse transform, just basically when I have low weights, I would take less number of samples. When I have higher weights, I would take more number of samples. Okay, that's what will happen. And we compute the final color equation, C fine of the ray R, using the union of both sets. So in the final rendering, we would use the coarse network location samples and the fine network location samples. N coarse plus N fine, we would use both of them. Now, the implementation details, how it is implemented. So the network architecture, it follows also another paper, which is Deep SDF, which we explained in the related work, signed distance functions, if you remember. Now, this is the network architecture. Here we have the input for gamma, which is the positional encoding, applied to X, which is the coordinate vector. It passes by 5 hidden layers. Afterwards, we notice something here. This is called the skip connection. So we have the same inputs, we concatenate them to the input of this layer. The skip connection usually is used in order to overcome the vanishing gradients problem. So they put the same inputs again here at this layer, and then they continue passing through the remaining layers. Now, here at this layer before the final one, they put gamma, which is the positional encoding, applied to D, which is the viewing direction at this point. And we notice here that already sigma, which is the density, it is output here. So sigma, like we mentioned in the first slides, that this is the multi-view consistency property, that sigma depends only on the position and it doesn't depend on the viewing direction. So, and the final layer, and we have from here the RGB output, which is the color that is dependent on both the direction and the position. So just to clarify also here, you notice that the inputs are 60. If you remember that we have the positional encoding, it's for X, Y, Z coordinates, and we have L equals 10 for positional encoding. So we have an equation of order 10. And for each one, if you remember, has a sine component and the cosine component. So 2 times 3 coordinates, this is 6 multiplied by L, which is 10. So this would give 60, and this is why also the direction is 24 inputs. Okay, so the training steps. So at each iteration, what happens? We randomly sample a batch of camera rays from the set of all pixels in the dataset. So we have a number of pixels in the input image, and we sample a chosen number, which is the batch size of rays. Each ray would represent 1 pixel. So we sample randomly a batch of camera rays from the set of all pixels. Now we follow the hierarchical sampling to query n coarse samples from the coarse network, n coarse plus n fine samples from the fine network. This was explained in the hierarchical sampling. Now we use volume rendering, which is the rendering equation, to produce the color of each ray from both sets of samples, n coarse and n fine. Now here, what's interesting is when we compute the loss. So this is the loss function. Also complicated just at the first sight, but when we break it down, so we are summing all the rays subset of R. So capital R is all the rays in each batch. R is our ray, is a small r. C of R, this is this term, which is the ground truth. This is the ground truth, the image itself that we are training on. And C of C and C of F are the outputs of the coarse and the fine network. So we have here, we calculate the loss on the coarse network output, and we calculate the loss on the fine network output. Now, we notice here that we calculate the loss for both. However, when we render just using the fine network. So why is that? So they explain it by, even though the final rendering comes from C fine of R, but during optimization, the loss of C coarse of R is also minimized to give better weight distribution of the fine network sampling. So they also optimize the coarse network in order to give better sample representation for the fine network. Like we mentioned in the hierarchical sampling, that n fine is derived from the probability density function of the weights, which are output from n coarse. So they continuously optimize both networks. However, the final output is just from the fine network. Pretty cool. So just to mention, because they were mentioned in the papers, the training parameters. So this model is implemented in TensorFlow. The batch size used was 4,096. They used 64 for the number of coarse samples and 128 for the number of fine samples. They use Atom Optimizer with a decaying learning rate from 5 times 10 to the negative 4 to 5 times 10 to the negative 5, and all other parameters are left at default. The optimization for a single scene typically takes around from 100 to 300K iterations to converge on an NVIDIA V100 GPU. This takes around 1 to 2 days, which is pretty long. So moving on to the results in comparison with other methods. Now, the results show that NeRF quantitatively and qualitatively outperforms previous work. So this is due to testing, which is done on 2 types of datasets. First is called the synthetic renderings of objects. This type of dataset is this dataset is taken from a dataset called Deep Voxel dataset. They used 4 objects from it: the chair, the pedestal, a cube, and a vase. These images are 512 by 512 pixels, 479 views as an input, and 1,000 views for testing. So, and there are 8 objects that they synthesized by themselves. The authors, they generated 8 new objects, chair, drum, a hot dog, material. You will see them in the results. Why? Because they are more complex objects than the ones that are present in the Deep Voxel dataset. They used from these 8 objects 100 views as input and 200 for testing. Now, the second type of dataset is real images for complex scenes. These are images captured by smartphones. They are 20 to 62 images for each scene. They are 1,000 times 756 pixels, 56 pixels. This is the resolution, and they use 1/8 of the images as a holdout for testing. 5 of these scenes were from the local light field fusion paper that we discussed in the related work section, and 3 scenes that they captured by themselves. Okay, so this is the data that they use to assess the NeRF method against other. So the comparison is done against local light field fusion, the neural volumes, and the scene representation networks. I guess we discussed all of them in the related work section. So first, this is the quantitative comparison. So this is diffuse synthetic. This is the deep voxel objects, the 4 objects that we mentioned. The realistic synthetic, this is the 8 objects that they generated by themselves, which are more complex 3D objects. And real forward-facing, these are the real images from smartphones, which part of them were used by local light field fusion paper. And here is the comparison as numbers. Now, just we don't need to explain too much what do these measurements, just try to think of them as some assessment measurement for the methods PSNR, the higher the better, SSIM, the higher the better, LP, IPS, the lower the better. So it is obvious that NeRF outperforms all of them on all kinds of data set, except for here, where local light field fusion outperforms NeRF in this metric. However, the authors, they mentioned that this is in the quantitative comparison. However, when you look at the qualitative comparison, it is obvious how NeRF outperforms them. So look at it now. This is the qualitative comparison. So this is the diffuse synthetic. This is 2 of the 4 objects that they mentioned. This is the realistic synthetic data set. So we have here 4 out of the 8 objects, and here they compare how NeRF, this is the ground truth, this is the input, this is NeRF output, this is local light field fusion, SRN, and near view output. And this is real forward facing. This is from the smartphone images. So we have here 3 scenes. And we can really see what they meant when they said, like here, we can see how the local light field fusion output is a bit blurry compared to NeRF output. So it's obvious here really from multiple outputs. So these are the results. This is the 8 objects that they mentioned, the ones that they generated by themselves, the authors, and this is the NeRF output for them. So again, I remind you that this is the output of the neural network. It is trained not on the object, or there is a 3D model that is fed. It's just a few photos, a few images of this object from different angles, and the network was able to generate all these continuous views of this object in 3D space, like you see. So it's impressive, really. So this is on the realistic synthetic, the 8 objects that they generated. Now, this is a comparison in the ship model between NeRF and the others. So we see here how SRN is poorly performing on this very complex scene, like we see. Local light field fusion, better, but still a lot of glitches and smooth textures appear compared to NeRF. Neural volumes, again, you can see how different performance between both. How here in NeRF, so small details are captured by the model that are not captured in neural volumes. So again, this is the drums scene. This is also comparison. And here is the nearest input image to what is being shown here. So we see again how NeRF model captures very small details in the image that other methods don't capture. And here, this is the real scenes, the ones in local light field fusion papers. We see how NeRF gives a good representation compared to other methods. Okay. Now for the ablation studies, this is part of the results. So the ablation study is to validate the choices that they made and the parameters that they used. So they did it on the realistic synthetic scenes, the age-generated objects. So the quantitative results, what did they do in the ablation study? Just to explain it quickly. Here, without positional encoding, without view dependence, without this hierarchical sampling optimizations, okay? So without hierarchical sampling, we would have just n coarse, we would not have n fine, so just one sample, one set of samples, I mean. There is no L. If you remember, L represents the order of the positional encoding. The number of images is 100, and there is no theta and phi because there is no viewing direction, just as a function of the inputs. Now here, it's without positional encoding alone. Here, it without view dependence alone. Here, without hierarchical encoding alone. So they do these tests. Here, they use far fewer images, 25 instead of 100. Here, they use 50. Here, they use lower frequencies in the positional encoding. So here, they use order 5. And here they use order 15. Now, it's noticeable also here that when you use higher frequency, again, when they reduced it to number 10, it does outperform even using higher frequency. So overdoing it isn't good in positional encoding. So this is the result that we get. Now to look at the quantitative results, so we have here, this is the true image. This is the complete model output. We see here when there is no view dependence, how this white is a reflection actually. So how this reflection doesn't appear in the without the view dependence feature. And here without the positional encoding, we see how everything is smooth and blurry. It didn't capture the fine details of the image. So this makes sense. And finally, for the conclusion, NeRF, it directly addresses the deficiencies of prior work that use MLP to represent scenes as continuous functions. This is what has been shown from the results and the conclusion. Now, representing scenes as 5D Euler radiance fields produces better renderings than training deep convolutional networks to output discretized voxel representations, which is the traditional or the old methods that were used. Now, the interesting part that I want to highlight, away from the results, NeRF outperforms the other methods in the following ways. So first, the SRN method, it produces very smooth geometry and texture, and its representational power of view is limited by selecting only a single depth and color per camera ray. So there's only one depth and one color for each ray, which, like we see in NeRF, it's important to differ between it depends on the viewing direction, and there are other limitations for SRM that are obvious in this. Now, near view baseline, it can capture detailed volume geometry, but like I mentioned also when we was in the related work section, it would require 128 power 3 voxel grid. It prevents it from scaling to represent fine details at high resolutions. So this is the downside for them. Local light field fusion, it can process a small input data set under 10 minutes, which is pretty quick. However, it produces a large 3D voxel grid for every input image. As an example, they mentioned here that it requires over 15 gigabytes for one realistic synthetic scene. So this is big for one scene to be represented. Now, on the contrary, when we see NeRF, it only uses 5 megabytes for the network weights. This is even less than the input images alone for any of the tested scenes. So this is really impressive, and this is why I think NeRF was a breakthrough in this area after I started reading about it. And finally, the list of all references here in the presentation and in the paper. And I hope you enjoyed it and understood what this paper is talking about. And thank you for listening and watching. Goodbye.